As said, I'm going to be talking about a unified gas and electric unit commitment, and we'll expand our discussion to looking at contingencies on generators in the electric grid, and this is part of our security gaps arising due to coupled energy delivery subsystems. Okay, so I'll start by giving a brief motivation for the work, which I think should be fairly familiar to everybody at CREDC. Then we'll go on to describe how we are modeling the gas network for our purposes, then describe the uncoordinated unit commitment, show where some issues arise there. We'll then demonstrate how we resolve that with a unified gas and electric commitment. We'll extend that to contingencies, and then I have some future directions that we're considering and conclusions at the very end. So as we've heard in numerous CREDC presentations, gas-fired generation produces a significant portion of the electricity grid, and as you look at the chart over here from the Energy Information Agency, its share has been increasing steadily, and therefore it is not acceptable for electric grid operators to neglect the constraints that this other energy delivery system imposes on their operations, and vice versa, though to be perfectly honest, we're looking at it very much from the electric grid perspective and how the gas grid imposes constraints on that area. So our main goals here are to come up with a unified way to solve this unit commitment problem of how generators are allocated, considering the constraints of the gas grid, and then extend that to contingency analysis, because gas generators are quite critical in the reserves for the electric grid. And as Anna mentioned, the tie to security is that we need to first build a framework where we can model how these two systems are interacting with each other. Then once we identify how that works, we can explore the different vulnerabilities and understand what are the impacts of targeting them. So that is the general framework we're working under. This is another interesting picture of how different areas create electricity, and you'll notice all the orange. And the one thing I'll point out, the simulations that we run are on fairly small generators. There are going to be these ones. I'll just point out that you actually see quite a few larger orange circles here, meaning that we're actually considered a fairly rosy picture. And things could actually get much more serious as you allow for larger and therefore more gas-hungry generators. So let's talk a little bit about how we model the gas system. We have a fairly simplistic view of it with four main components. We have gas wells and storage, which are points where electricity is inserted into this, not electricity, sorry, gas is inserted into the system. There are the pipelines that then transport the gas from between different points. There are compressors at certain places that control the pressures and therefore the flow. And finally, you have different demand points, and essentially we'll be modeling gas generators as demand points. So we're considering, for the purposes of this presentation, a one-dimensional steady-state formulation. And when you look at things in that way, then you basically have a relationship between the square of the pressures at 2 points in the pipeline with the square of the flow and some constants that account for friction, diameter, etc. And the thing to notice here is that we have this relationship with the squares, and there's the sign of the flow, and that will be a lot of what we focus on in our formulation, is how to unpack this sign function here. I included the units here just for reference as we move So the basic formulation of the optimal gas flow is as follows. We have the gas generation, this G at a particular time point at a particular well times some price for producing gas at that location. And we are introducing something here which is a gas reserve, and you can think about it as a certain headroom that a particular generating point is allowing itself to have so that it can potentially increase some more. And this is not necessarily often seen in these sorts of formulations. It mirrors a little bit the electric reserves, and I will get to some of this at the very end when we talk about future directions. So keep this reserve point in mind. So then we have a few constraints, which is namely that a gas well or source point has to produce a certain amount. It cannot produce infinitely small amounts. And the total amount that it produces plus this headroom reserves that it is leaving must be below its maximum possible output capacity. And then we have a nodal constraint where the sum inserted at a particular node plus the sum flowing into that node from pipelines where this node is defined as the to node of the pipe minus the flow going away on pipes where this node is the from node is equal to the total load. So that is the load that is consumed at that node. And then we have the constraint on the flow that relates to the compression ratio over here. So we have the square of the pressures, the flows, and then this alpha is just saying where along the line, percentage-wise, so if you just put this to 0, meaning it's at the very beginning of the line, then you have the standard compression ratio equation. And finally, we have pressure limits on the pipelines. It must remain within a certain boundary. So just again, a note on the compression ratio. We assume it's greater than 1, and that's where the sign exponent comes here. And it is given as a parameter. So we're going to not let this vary, but rather say it is fixed at a particular thing, which essentially fixes also the direction of flow in those particular edges, which we will refer to as active edges. And you'll see 1, then you have a normal line. So actually, let me step back. This formulation is fairly nice and linear and friendly, except for this messy equation. So what we're going to do now is try and look at ways of tackling this constraint and to make the problem more solvable. So if we assume that we know the sign of the flow and that it is positive, we can change the equality to we can constrict the flow between these two square root terms. We've essentially just solved for flow from the previous equality. The other option is that the flow is negative, and then again we have this we solve essentially the other options. And what we've done here is then essentially mapped our pressures into squared pressures, which is not a problem since pressure is a strictly positive term, or strictly non-negative rather. And we have essentially converted in this way a pressure limit to a flow limit. Okay, so the key point is that the nonlinear constraint is mapped onto 2 linear constraints. These are now essentially known terms over here, these gammas. And the mapping is 1 to 1. So we haven't actually made any simplification. However, we still have this if-else statement that we need to address so that in the optimization we know which constraint to account for, and that's what we look at next. So what we do is basically create disjunctive constraints. We decompose the flow. We say that it is both a flow in the positive direction and a flow in the negative direction, where both of these now superscripted f's are strictly positive. And we introduce a binary variable for each edge that is 1 if the flow is positive and 0 otherwise. And in this way, we can introduce the following constraints. We have that the flow on a line K in the negative direction is 0 for edges that we're calling active. These are the ones with the compressors, since, again, recall that a compressor forces flow in a particular direction. So there, we do not have to consider which way gas is flowing. And the limits on flow are these gammas that we derived in the previous slide that had to do with the squared pressure, times this, so these are known constants for a given line, and times these binary variables. And in the other direction, in the negative direction, we have times 1 minus these binary variables. So, for example, if z is 1, then this will impose the necessary limits on the positive flow, and the negative flow will be forced to be 0. And if z is 0, then we have the other situation. So a fairly standard disjunctive constraint formulation. So the pro is that we're now implicitly, through these binary variables, considering the flow direction. The con is that we have introduced binary variables, which make the solution process more difficult. And we have needed to introduce all these, we basically have doubled the number of constraints for flows. So, however, we now have a mixed integer linear program that we can solve. So let's move into the case formulation where we test what this, how this behaves. So we use a slight modification of the Belgian gas grid, which was presented in this paper by De Wolf and I believe it's Schmeers, but I'm not, don't hold me to that pronunciation. And just, I was slightly confused. This line over here, if you can see my cursor that kind of moves around, is the boundary, is the border of Belgium. It's not actually a line. So this is a radial grid. And you can see it has two compressors and 6 different gas wells. And in the following slides, we'll report cost for the optimal gas flow. The cost that we were using for a cubic meter is this in dollars. Obviously, they use euros in Belgium, but we're just, we decided that they will use dollars for our purposes. So when we run the simulation, these are the results that we get. You can see the compressor settings over here. Things are pretty flat, which is to be expected since there's not a whole lot of fluctuation in the gas system. More than anything, this just shows that we have a stable solution, and we can now move on to considering the joint problem with the electric formulation. So now we're going to start combining the gas and electric unit commitment, and I'll just point out, I don't go in this presentation into detail about the electric unit commitment, partially out of the assumption that that has been covered more frequently, but I'll be happy to answer questions about that at the end if anybody has that. I realize that that is not as explicitly stated in these slides. So we make a few assumptions in order to make the conversion between electricity and gas. We assume that we assume that a cubic foot of natural gas has contains this many BTUs. This is then the conversion to megawatt hours, and then we're for the electric grid we use the RTS 96 system. I have a picture of that coming up in a couple slides. And we took the 50 megawatt generators and treated them as gas-fired combined cycle turbines with efficiency of 50%, and the 20 megawatt generators are treated as strictly gas-fired turbines with an efficiency of 35%. These are not the original turbines in the system. There are actually no gas turbines in the RTS system, so we just made these assumptions, which seemed reasonable. And using this, we can then convert power in megawatts through some dimensional analysis to a gas load, which will be in meters cubed per hour as defined previously. We keep the compressor settings at the same place, and then for those of you familiar with the RTS-96 system, these are the connections between that we make between the RTS and the Belgium grid. In terms of numbers, this is not very revealing, but you can see that we have basically 4 gas nodes that are connected to 4 different buses. I think this picture is slightly clearer of how we're connecting here. Just note that these generators that you see here are actually either 2 or 3 generator sets that we're then considering. So that is the test case, and for the uncoordinated case, what we're going to do is solve the electric grid unit commitment and then simply convert the powers of gas-fired generators to gas load and solve the gas flow. And when we do that, so that's this sentence here, when we do that, what we see is that our generators are dispatched in the following manner. And that when we look at some of the pipelines, we have violations of the flow limit, meaning that the generators should not have been dispatched to such a large amount. That capacity was actually not there in the gas grid. And this is, just to put things in context, fairly consistent with some other work in literature that has shown similar constraints, and is an obvious motivation for now creating a unified formulation, which comes next. So what we have in sort of schematically for the unified gas and electric unit commitment is we're trying to minimize for all time points the cost of producing gas. So this GW is the gas injections at the wells or storage sites, and the cost of electric generation and the electric reserves that we're committing, subject to the gas constraints that we went through briefly, including this mixed integer linearization and the standard electric unit commitment constraints. And then the one thing that we do is we modify the nodal balance equation over here and introduce this term where this eta is the dimensional analysis that I performed 2 slides ago that converts the gas generation at the power generation at gas-fired plants to a gas load. So this is the single coupling equation between the 2 systems. And when we now solve this, we see that we have no violations. You'll also note that the gas generators are committed far less, which then manifests itself in a slightly higher price. However, this is now respecting the constraints of both systems. So while it is somewhat more expensive and maybe utilizes these generators a little less, it is a feasible solution. So kind of keeping in mind things in terms of security, if you somehow do not account for this correctly, or you maliciously make sure that this is not accounted for correctly, you could have schedules that are not possible and could not accurately be carried out. Now, actually, I'll step back. It's interesting to note that these generators 1 and 2, for example, have not been committed at all. And that is actually not so surprising because a lot of small gas-fired generators are not committed to supply base load, but are rather committed as reserves, and in particular non-spin reserves because they have a very fast ramping capability. And this is what led us to consider to extend this analysis to generator contingency, because gas-fired generators provide much of the non-spinning reserves and are therefore critical during these situations, but the added power that they're now going to be supplying, and therefore the added demand on the gas grid that they're going to withdraw, has to be by the pipeline constraints. And so what we need to do is add more constraints. So we add the following constraints to the typical generator contingency analysis, where C is a particular contingency. So for a particular C, we assume that a generator has failed. And so if you recall, we had these RGs, which were these reserves in the gas grid, which are essentially some headroom that has been left. And with the superscript C, that is what is actually being activated during the given contingency, and that obviously cannot be any greater than what has been pre-allocated. And this constraint over here is simply a balance of the amount of reserve electricity generated by gas-fired power plants times this conversion factor has to equal, or should equal, the amount of added gas that is flowing in the pipeline due to this contingency. Then we modify again the nodal balance equation to include this added variable in the power inserted into the gas grid and in the power withdrawn at the gas-fired generators. And finally, we have to adjust the flow, or we have to add more flow constraints as well, since depending on on which generators are failing or where new gas might be coming into the pipeline, things could theoretically change. So these are the exact same constraints as before, but for the flows in this particular contingency. So that is the adjustment we make to the formulation. For the test case, we modified slightly the mapping between the gas nodes and the RTS bus nodes. So just for reference, again, numerically, this is what it is if you're familiar with the RTS case, and schematically, that is what this looks like. And then when we perform the simulation, we get the following results. So in this first plot over here, we're looking at a particular contingency where generator 90 in the RTS case has failed. It's a fairly large generator, and we see at how the different generators are responding. And then over here, we see the value of these reserves at the different gas wells, and we see that they are following the behavior of the gas generators, which is to be expected. That is essentially those constraints that we just added. That is what they require. I'll just make a side note. I don't have a plot for this, but we did a separate test where we simply considered what if all the reserves at a particular set of gas generators would be called up. What would that mean for the flow on the pipeline that is supplying them? And we saw that in fact the pipeline hits its limit, but it does not exceed it, which was a good sanity check that the optimization was working correctly. So the gas generators have not procured more reserves than they are actually capable of delivering given the constraints of the pipeline they are connected to. This, however, brings up an interesting point because we're now basically looking at the connection between when gas is inserted into the grid and when it is withdrawn. And this brings us to the future directions that we're looking at. So the first one is considering some of the dynamics because line pack is slow. As Al and Shabir actually were talking with me during the last meeting at PNNL, it can take close to half a day to pack a line to a particular pressure, and therefore the idea that gas is consumed and generated at exactly the same time is not feasible, and the minute that we accept that, we have to consider the dynamics of how my withdrawal at a particular point needs to be anticipated by production somewhere else in the network. Something that I heard from a professor here at ASU with regards to that is what happens when you have a quick step change by a gas-fired generator. So what he was claiming is that you often see that the generator spikes up and then sort of sags down until the pressure in the pipe is recuperated. And then the question is, how quickly does this happen? If these dynamics start to overlap with the time steps that we're considering for our steady state formulation, then we have a contradiction, and again, we need to consider these dynamics. So that is one future direction that we are considering to find a vulnerability, which again, once we discover the vulnerability, that can be mapped onto different security and cybersecurity concepts. The second direction that we're looking at is comes more from the component failure perspective. So we're very used to thinking about N-1 contingencies. It's exactly what we just showed in terms of generator contingencies in the electric grid. However, if we have a single failure in the gas supply system, that can lead to a set of contingencies in the electric grid. And so we need to consider specific sets of N-many contingencies. And this is actually suggested in a NERC report, I cite it down here, from 2013 about reliability assessment. And sorry. So they mentioned something similar, although I did not see in that report that they addressed what to do about this. So we're trying to understand what is an appropriate way of modeling this and taking this into account, all the while realizing that there is one solution to all of this, which is to simply say gas generators shouldn't be relied upon for anything, but that is clearly not a viable solution. So we need to find the happy medium. And the other thing that I find interesting about this particular approach is that we don't have to assume that the compressor totally fails, but rather just that there is a particular lack of a particular decrease in capacity that impacts simultaneously multiple generators. It's possible that simply reducing the capacity by some is sufficient to cause something equivalent to a contingency. So this is the other direction that we are considering. In conclusion, what we have shown is that violations in the gas grid limit, in gas grid limits are caused due to uncoordinated planning between the electric grid and the gas system. And therefore, this needs to be rectified, and we proposed a unified mixed integer formulation that is capable of doing that. And then we took this formulation and extended it to generator contingency analysis, given the fact that gas generators are particularly important to the electric grid in the contingency setting, and therefore we want to make sure that the reserves that they are promising can actually be supplied in terms of their fuel. So those were more or less the points that I wanted to cover. Thank you very much, and I will gladly take some questions. There are some references here for if anybody is interested. That's it.
Okay. So we're unmuted here at Illinois, and others who have questions that are not at Illinois, you'll probably need to unmute yourself to ask the question. The floor is open.
Sure. This isn't a question exactly, but you mentioned the effect of using the gas compressor and how that it would spike up and then sag down and so on. You'll get different performance curves depending on whether you're using a reciprocating compressor or a centrifugal compressor. Generally, the centrifugal will give you somewhat smoother operations, but it doesn't have as great a compression range within a given computer or compressor.
Yeah. So to be perfectly honest, I don't know that much about the mechanics and the different designs of compressors. This came from a professor here at ASU that does a lot of testing of gas generators specifically, and he said this is something that they frequently see when they do a step test on a generator, that they have this, the way he put it is they're very happy to comply with your step test, but then they sort of ramp down a little bit because they don't immediately have the fuel. Now, the thing is, I've not yet been able to find these curves to analyze exactly what's the rate at which this comes back. But this is something we're trying to work towards looking at a little bit more clearly. But thank you for that.
Sure.
Hi, it's Dylan Rodrigo. Got a question for you. Would you consider in a future iteration to look at incorporating a second dimension or another dimension in terms of like how weather impacts both the gas and electric grids?
So I guess short answer is yes. Longer answer is the way this I would imagine this playing out is that the loads in both systems would tend to increase as the weather gets colder, and
right.
so you get a higher demand, and at higher demand, all your systems are more taxed. That comes back a little bit to what I was saying in terms of the slide on if you have a failure in the system, you can think of a failure as a derating, right? So one option is to just say, how much capacity do I have available for gas-fired generators? And if all of a sudden everybody is heating their homes very excessively, then I have less capacity. This is, I believe, that in New England they have had certain situations where actually the gas-fired generators were not quite able to get everything that they wanted on particularly cold days. So short answer, again, yes, we will consider that.
Thank you.